So still on the topic, or under the banner of the power set axiom, now that we can define the Cartesian product of sets, we can also define a relation. And in fact, you should recall that a relation is any subset of the Cartesian product. Now, to give an example, maybe as a refresher, we can look at the relationship of less than. Now, this will be the set of all ordered pairs such that the left coordinate is less than the right. I'll take, for my example, the natural numbers, which we don't know exists. Of course, right, even to this point in the development, we still have not learned that anything actually exists, but we will eventually, and so supposing that we have defined the natural numbers, the less than relation on those natural numbers is exactly equal to this set of pairs where the left coordinate is 0 and the right coordinate is anything, or the left coordinate is 1 and the right coordinate is 2, 3, and so on. So the set of all of these ordered pairs is equal to the less than relation. So the relation is indeed a subset of the Cartesian product. Now we can also talk about the domain of a relation, which, if you recall, since we had to take power set twice, then the domain of a relation we denote this way, and it's going to be a subset of the double union over that relation, right? So the double union is to take care of the fact that we are dealing with sets of sets of sets and so on. So, and similarly, the range is also going to be a subset of the double union over the relation. We can define it rigorously, but basically the domain of a relation is just the set of all left coordinates. The range of the relation is the set of all right coordinates. Okay, that's domain and range. We can also define the notion of a function, and a function is a certain kind of a relation, right? We call something a function just in case for every left coordinate there is exactly one right coordinate. So, the y is related, if y is related to x by y equals x plus 1, this is a relation. It's determines a set of ordered pairs. So the set of ordered pairs would just be 0, 1, and 1, 2, and so on. And you can include more if you want to account for negative numbers, rational numbers, and so on. But in this relation, because you only ever see 0 in the left coordinate when you see 1 in the right coordinate, that makes this a function. This is a function, again, because if any two pair have the same x coordinate, they must have the same right coordinate, right? Because if you ever pick another ordered pair out of here and it has 0 in the left coordinate, it had better have 1 in the right coordinate. That's what makes this a function. Yeah, we have defined the notion of power set, the notion of the Cartesian product of sets, the notion of a relation, functions, and we can also talk about the set of all functions. The set of all functions f that map from x to y, we will denote by y to the x. So that is the set of all f such that f maps x to y. A bit of a weird redundancy of notation here, but that's the intended grouping. So, okay, on to the next axiom.